Hello, everyone. In the final phase of our project, we revised our EDA and uncovered several key insights. First, the data is highly imbalanced, with 92% of applicants successfully repaying their loans. Most clients were laborers, while the fewest were IT and HR professionals, which is typical for low credit history applicants. We also observed that individuals on maternity leave or unemployed individuals had the highest default rates, while those with academic degrees had the lowest. A primary challenge with this data was combining static and time series data with careful alignment and pre-processing, which Cassie will now explain as part of our modeling pipeline.
Thanks, Nasheed. For our modeling pipeline, we started by consolidating data from diverse data sources into a single data set and engineered features based on EDA and business understanding. We transformed categorical and numerical features, then reduced the data to 20 features using PCA, feature importance from decision trees and random forests in correlation analysis. We tested both the complete and reduced feature sets using models like logistic regression, random forest, decision trees, gradient boosting, extreme gradient boosting, and light gradient boosting. Finally, we applied ensemble methods, including stacking and voting, and performed hyperparameter tuning to optimize the best performing model. XGBoost was selected for its high accuracy, 91.59%, efficiency, and scalability. However, it struggled with severe class imbalance, evident in its low recall of 0.94% and poor F1 scores for the minority class, as shown in the confusion matrix. Maria will talk about our implementation of MLP next.
For our MLP experiments, we tested various architectures, including sparse input MLP for benchmarking, simple deep MLP for added depth, an MLP with dropout to reduce overfitting, and a wider MLP. While the results show only minor differences across architectures, all models were trained using PyTorch Lightning with a pipeline, preprocessing strategy, and GPU acceleration. We used the Atom Optimizer with a learning rate of 0.001 and trained for 20 epochs, monitoring validation accuracy for checkpointing. TensorBoard provided insights into training metrics, helping us refine the models and evaluate consistent test performance across the different experiments. We found that MLP models did not show a significant improvement over the other models, such as XGBoost and LightGBM. Most importantly, the class imbalance issue persisted across all MLP experiments. These results have been submitted to Cagwin, and Lexie will now tell us about next steps.
Thanks, Maria. To wrap up, many of our models performed similarly regardless of feature selection, and while MLP models were comparable, they didn't outperform the other approaches. A major challenge was the class imbalance of the dataset, which impacted our ability to effectively model the data. Our chosen model excelled at predicting non-defaulters, helping to avoid unfair rejections, but struggled to correctly predict defaulters, posing a risk for lenders. To address this, we recommend using methods like SMOTE to generate synthetic samples for the minority class, cost-sensitive learning or ensemble techniques like balanced bagging or boosting. And throughout our project, we faced additional challenges, including the complexity of dimensionality reduction, computational limits with Google Colab, and coordinating edits among team members.